Welcome to the deep dive. Today we're taking a look at a really fascinating source document. It's all about constructing geometric shapes.
Yeah, and doing it with just the bare essentials, a ruler and a compass.
Yeah,
Nothing else.
exactly. So our mission here is to kind of unpack the core ideas. How specific bits of information, like maybe side lengths or angles,
Diagonals, yeah.
let you precisely pin down the vertices, the corners of these shapes. We're talking quadrilaterals, hexagons, you name it.
It's about following the roadmap that geometry itself provides, using just those two tools. Pretty fundamental stuff, really.
Okay, let's dig into the source material then. It starts with quadrilaterals, the four-sided shapes. And right away, it seems like the given info dictates the whole approach.
Absolutely. Take the example where you have four sides and one angle given.
Right.
You'd start by drawing one side, then constructing that given angle at one end, measuring out the next side along that angle line.
And it's good out. How do you find that last fourth point? That always seems like the tricky part.
Well, this is where the source highlights something quite clever. Often, building a quadrilateral actually relies on building triangles first. So in that four sides, one angle case, after you've placed the first three vertices, you've basically got two sides left. You use your compass, set to those lengths, and draw arcs from the known endpoints, where the arcs cross. That's your fourth vertex.
So you're triangulating that final point, sort of.
Exactly.
Yeah.
Triangles are stable, rigid. You're breaking the quadrilateral problem down. Think about another case. Four sides and a diagonal are given. You don't just draw the diagonal in space. The source shows you use the diagonal and two sides to construct one triangle first.
Okay.
Then that same diagonal becomes a side for the second triangle, using the other two side lengths. You build a quadrilateral piece by piece, triangle by triangle.
Right, that makes sense, breaking it down. Now, this gets really interesting when applying it to specific shapes, like parallelograms.
Yeah.
The material says properties are key.
Oh, definitely. The properties are like built-in shortcuts. For parallelograms, the big one is that the diagonals cut each other exactly in half. They bisect each other.
Right, at their intersection point.
And that's super powerful for construction.
Yeah.
Let's say you're given one side, BC, maybe 4.5 centimeters, and both diagonals, AC 5.6 centimeters, and BD 5.0 centimeters.
Okay, seems like you're missing angles or something.
You are, but you don't need them. Because the diagonals bisect, you can focus on the intersection point, let's call it O. You know, the distance from O to B is half of BD, so 2.5 centimeters.
And O to C is half of AC, so 2.8 centimeters.
Exactly. So you can construct triangle OBC using side BC, 4.5 centimeters, OB, 2.5 centimeters, and OC, 2.8 centimeters. You build that central triangle.
Ah, I see. Once you have O located relative to B and C.
You just extend the line segment BO past O for another 2.5 centimeters to find point D, and extend CO past O for another 2.8 centimeters to find point A.
And boom, there's your parallelogram. That's elegant. It uses the property directly.
It's a fantastic example of leveraging a known characteristic.
So what about other shapes? Rectangles, rhombuses, squares, similar ideas.
Similar, but they use their own specific properties. For a rhombus, the diagonals don't just bisect. They do it at a right angle. That's crucial.
Okay, and 90 degrees.
So if you're given the two diagonal lengths for a rhombus, you draw the first diagonal. Then you construct its perpendicular bisector that gives you the midpoint and the right angle.
Got it.
Then you measure half the length of the second diagonal along that perpendicular bisector, upwards and downwards from the midpoint. Connect the four endpoints, and you have your rhombus.
And squares are like that too, because their diagonals are equal and meet at right angles.
Precisely. Same principle, just with equal half-diagonal lengths.
What about trapeziums with those parallel sides?
The parallel sides are the key there. Often the construction involves sort of shifting a line or creating an auxiliary triangle outside the main shape that helps you determine an angle or locate a vertex, exploiting that parallelism.
Okay. And finally, regular hexagons. The source mentions multiple ways, but one sounds particularly neat.
Yeah, the circumcircle method, it's brilliant. It relies on this amazing property. Yeah. For a regular hexagon, the side length is exactly the same as the radius of the circle that passes through all its vertices.
Wait, really? The side equals the radius?
Exactly. So the construction is incredibly simple. You want a hexagon with a certain side length. Draw a circle with that side length as the radius.
Okay.
Pick any point on the circle's edge. Now, keep your compass set to that same radius. Put the point on your starting vertex and make a mark on the circumference. Move the compass point to that mark, make another mark, and just walk the compass around the circle.
6 steps, and you're back where you started.
6 steps get you exactly back, and those 6 marks are the vertices of your perfect regular hexagon. It's a direct geometric consequence.
Wow. Okay, so Stepping back, what's the big takeaway from all this? It's not just drawing practice.
Not at all. This deep dive really shows that construction with just a ruler and compass is fundamentally about understanding the essence of each shape, its defining properties.
Right, and using those properties, along with basic geometric tools like triangle construction or finding midpoints.
We're using bisection or perpendiculars.
Yeah.
You use that logic to turn a few given pieces of information into a precisely drawn figure. It's the art of deduction, really, applied visually.
It definitely highlights that elegant link between the abstract math properties and the physical act of creation. It makes you appreciate how constraints, just these two simple tools, force you to be clever and rely on the fundamentals.
It really does. And it leaves us with something for you, the listener, to think about. We've seen how different sets of information allow construction. So consider this. If you're given just 3 pieces of information about a general quadrilateral, is that ever enough to construct it uniquely using only a ruler and compass? And if it is, what kind of 3 pieces might work? Something to ponder.